Okay. First off, I'd like to thank the organizers for setting up this meeting before Amplitudes and for giving me a chance to talk about my recent work with my supervisor, Fernando Alde and Shinan Zhao. So today I'm going to be telling you about bootstrapping string scattering off D-Branes in AdS. So the question that we want to address is, can we compute string scattering either form factors when we have D-Branes or more generally in work that's already been done, amplitudes in AdS without quantizing the string in AdS, because that's hard and it's easier to not do hard things than to do hard things most of the time. So the sort of ideas that we're going to be thinking about are, you have a string coming in, some D-Brane, strings going out, but people hadn't previously done this for just a bunch of strings together. And of course, the answer to this question is yes, otherwise I would be giving a very short talk. And of course, you might think that AdS CFT gives you the answer, right? So Witten, Maldacena, they taught us about AdS CFT, and you might say, okay, well, from the CFT, I just take whatever the equivalent of conformal blocks become in AdS, and I sum of those multiplied by some OPE coefficients, and that's the answer. Which is great until someone asks you what the coefficients are, at which point you will look at them with a blank smile and not know what to do. But there is a key insight, which is that in the pure AdS side, we expect there to be some world sheet. Therefore, we expect that there exists some integral of this form with some function g that's currently unknown, which should be able to reproduce this same thing, right? So we should get some function of our momenta squared s and q as equal to this integral and as equal to this thing. And you might hope that both of these together somehow gives you an answer. That's still pretty hard. So what you do is you work in the flat space limit, and it becomes some tractable bootstrap problem, right? Where you, let's say we know the flat space answer, you want to go to the next order. Can we use the fact that we know this, that we know some of these things, to sort of build our way up to the next order? Well, the answer is going to be yes, as it turns out. The approach that I want to take here is I want to take the bootstrap approach, which is I want to answer the question, if we can't compute our answer directly, what do we know, right? What are we able to do? And in any bootstrap question, you will essentially be asking what are the structures of the answer and what are the coefficients in front of those structures. And so I'm going to start telling you what those things are. First off, from AdS CFT, we know that 1 over root lambda, which is the 't Hooft coupling, is 1 over r squared. So what we want to do is some large coupling expansion. So this gives us the regime in the CFT at which we need to look for our original question. We know the flat space limit. For example, Hashimoto and Klebanov in the late 90s computed a generic form for these. So multiplied by some essentially kinematic prefactors, it's this ratio of gamma functions that looks like the Veneziano amplitude and is the same function as the Veneziano amplitude, but there are branes involved, so we don't call it Veneziano amplitude. This gives us what operators show up in flat space, and it gives us their OP coefficients just by matching to the expansion that we had before. And we also know the supergravity amplitude. People have bootstrapped this. So what that gives us, of course, supergravity being the massless limit of string theory, this gives us the poles for mass 0, right? String mass equal to 0 in this amplitude. So we have the 1 over r squared correction to that only for s and q being 0. We also know that the massive poles should come as the flat space limit of the CFT, which we're going to take from melon space. Fernando and Shinan having found a formula to go from melon space to essentially its flat limit in the defect case. And we have an ansatz for the world sheet that has been previously studied in some older papers. Okay, so now I'm going to sort of split the talk into first the CFT side, then the AdS side, and then we'll come together at the end to do AdS CFT, match everything, and get our final results. I apologize for everyone for inverting the acronym to CFT AdS, but that's just how it's going to be. All right, so if we want to focus a specific tractable field, we're going to study line defects in n equals 4 super Yang mills. This is dual in the bulk to an interaction with a D1 brane, right? So I'm going to write a defect correlator as this double angle. Essentially, it would be the 2-point function multiplying a defect divided by the 1-point function of the defect. But for other dimensional defects, it's slightly different, so I didn't want to write that. And you extract some just necessary things for the invariance under the relevant conformal group, and you get something which is a function of your usual space-time cross ratios, which are slightly different for the defect case. And this is the R symmetry cross ratio, which essentially encodes the R symmetry invariance. Then you lose the ability to control your.
Yeah, right. You can click on the window. Yeah, right click.
And this should, there we go. So we want to work in melon space, as I alluded to before. Melon space, for those of you less familiar with it, is essentially just this integral transform. It looks a little bit scary, but if instead of power laws here, you had exponentials, this would essentially just be a Fourier transform. So this is just some integral that you can do. And these gamma functions just encode some universal poles, and the dynamical information, the equivalent of this, is held down here in what we call the melon amplitude, which depends now on these delta, gamma, and sigma. Okay, and yes.
The delta into the capital delta, into
Yes.
those are the dimensions of
Conformal dimensions of O1 and O2, which we're going to set to 2 because we're interested in the stress tensor multiplet very shortly. So the sort of functional structure of M is as a sum of residues. So in melon space, it's sort of like what you would have in momentum space for a regular QFT. You have poles at the exchanges of variables. Here, the poles are written as sums over conformal descendants. So you get essentially for a single exchange of a conformal family with a specific dimension and spin, you get one function that encodes everything with all the conformal descendants. And you can expand this in 2 different channels, where you can either have the 2 operators meeting in the bulk and exchanging a particle with a defect, or they each meet on the defect and then they exchange some particle that lives on the defect itself. And the poles for that are either respectively in delta or in gamma. And essentially, well, we don't have crossing symmetry, which is the thing that you would normally hear me tell you about during a Bootstrap talk. We have these 2 different channels that are going to have to be equal, but they're not related by just exchanging delta and gamma. So we don't call this crossing symmetry. And we once again lose. Go. So one last thing that we need to worry about in terms of this, I showed you how we deal with the position space, but I didn't tell you yet about sigma. So in order to deal with sigma, there is still something called a superconformal word identity, which this function must obey. So f and m are quadratic in sigma if you set, if you're interested in this line defect thing that I was talking about with delta I equal to 2. And they have to obey this differential equation. These are just modifications of the cross ratios to get a very simple differential equation, which is evaluated at alpha equals z, and that's equal to 0. And that looks quite difficult, but if you look, a differential equation just takes those power laws, basically derivatives shift the power laws by 1, so you get a difference equation in melon space. Now, a difference equation still looks like something pretty difficult, but you can actually show that there exists a universal answer to it, which is to say you have some operator that's formed of shifts, and then some unconstrained thing, which you can sort of think as your initial conditions, which generate all anything of this form is going to be a solution to superconformal word identities. I showed last year that if you work in some basis that diagonalizes shifts, essentially the basis of power laws, for essentially most superconformal field theories that I've been able to write down, you are able to find such an operator D when you're working in melon space, and so the superconformal word identity has some very simple solutions, and you just have to worry about this simpler reduced function. Okay, now we can move on to the flat space limit. So as I said, Fernando and Shannon showed that there exists just some integral transform which relates the flat space limit to the amplitude that we had before in position space. So you rescale your delta and gamma by r to go like r squared. You expand in r squared, and then you can just do this transform with some ansatz, and you can find the flat space representation, the flat momentum space representation of that thing that we had before, and you can just build this in 1 over r squared perturbatively, assuming that this integral continues to hold. So D that I showed before gains an expansion as an operator. It's very easy to invert. In fact, it becomes just algebraic. And so you can use the reduced form for everything, and you don't have to, you can just factor out completely the dependence on the supersymmetry. And what you get now is a structure that looks like this. So at first order, you get the very familiar, you get like just simple poles with some residues, which you can get from those polynomial residues that I showed before. And at the 1 over r squared, you get poles of order 4. And it's going to be very important that these are poles of order 4, because that's what's going to tell you what to put in your world sheet when we finally get to AdS on the next slide. So I'm going to pause here because that's the end of the CFT side, and ask if there are any questions on the setup so far. Okay, then we can look in AdS. So in AdS, we want to have a world sheet form. We want it to be as a sum of objects like this, but we want these functions to not just be function, because, well, you can't just integrate function, right? You have to have some functional dependence. So thankfully, people have done this before, and essentially, due to some number theoretic concerns, you can find that the special functions that can show up in these integrals are what are known as multiple polylogarithms. Multiple polylogarithms are indexed by a word w, which contains just zeros and ones, and obeys this differential equation. It looks really complicated, but if you just set a equals 0 here, and this to be empty so that you have just 1, this is just the differential equation for the logarithm, right? And so you can iteratively build from there. So L00, for example, goes like log squared over 2. If I had put a 1 here, it's like log of 1 minus x. And then you get polylogs like Lie2s, you get log time log, you get a bunch of structures, but these are fairly simple to build iteratively. And then you just have some polynomials which have a homogeneous degree. You have polynomials of homogeneous degree, which is to say always of the length of the word plus 1 divided by this particular pole that you input to be able to reproduce the supergravity pole. And then and it's linear in x. That's slightly different from this project compared to previous ones. It's essentially due to the lack of crossing symmetry that you, as far as we're able to understand it. And then you have this zeta part, which is just zeta values multiplying more polylogarithms. Essentially, zeta of 2 counts as a word of length 2, zeta of 3 counts as a word of length 3, just because, again, of the number theoretic properties of the polylogs that I alluded to earlier. And the sort of interesting thing about that is this here. Why are the words of length less than or equal to 3? Well, as I said before, we had poles of degree 4. Right? So if we had poles of degree 4, if you look here, inserting a log is like a derivative with respect to s, right? So if I differentiate this with respect to s, I generate a log. So log cube, acting on the thing after you've integrated it near the pole, takes a single pole to a 4th order pole. So the highest weight that you need to be able to reproduce the pole structure is weight 3. Okay, and that's what I'm saying here. So you build this ansatz. And then it's time to do AdS SEPnet that I promised you towards the beginning of this talk. So if we now go, we can match pole by pole compared to the Mellon space results. So we can solve for these polynomials by just inputting some arbitrary degrees, and we can also solve for CFT data, right? So as I said earlier, we don't know what the spectrum is. At flat space order, we were able to find it just from matching to those gamma functions, which have poles in some specific place, but now we have to find the anomalous dimensions and things like that. So pole by pole, you get different amounts of CFT data, right? So the fourth order poles, you get informations on the polynomials only. At the next level, you get the polynomials on the spectrum, and you get the spectrum, the polynomials, and the OP. And the reason for this is essentially that the spectrum, as we said, the poles are at s minus 2n, so that n comes from the non-anomalous dimension, the base dimension delta. But then when you have a 1 over r squared correction to that, if you just Taylor expand that pole, you get a second order pole. So you essentially get like anomalous dimension times the 1 over r squared you get the anomalous dimension times the second order pole, and then the OPE coefficients are multiplying the thing, so you just get the flat space result times the 1 over r squared OPE coefficient that shows up, and that shows up only in the simple poles. And then perhaps the most interesting thing I can show you, rather than flashing an incredibly long list of polynomials at you, is the new CFT data that we're able to get that's currently unavailable from other methods that might be able to compute this one day. So things like integrability or other forms of defect bootstrap, things like that. If we look at the delta in the defect channel, because in the bulk channel it was already known, so here I'm setting the spin to be n minus 1, which is to say the first red-jet trajectory, so the lightest operators that are going to be showing up, you get this as the anomalous dimension. Okay, so that's some numbers, but we're of course expanding this forever. I'm able to tell you, I would in principle from the amplitude that we fixed, be able to tell you all of the anomalous dimensions, at least average when there's degeneracies over the quantum numbers of that degeneracy. Okay, and finally, there is an independent check on this. So this is not just me, doing expansions in Mathematica and then speculating wildly about what the results are. You can check the higher derivative corrections to Sugra from a localization calculation that had been done previously by various other authors, and this gives you something that you can verify our results against, that you know that we're not just making it up completely. Okay, so now that we're done, I want to just take a brief moment to talk about the outlook a little bit. So what we did is we extended the AdS Virasoro-Shapiro or AdS Veneziano bootstrap, which is this business of comparing to a worldsheet, in order to consider the interactions of strings with D-Branes in AdS. We obtained new CFT data for n equals 4 superyoung mills in the presence of line defects, as well as the new amplitude. And finally, I want to tell you a bit about our future directions, some of which we've started, some of which we haven't. So I'm hoping that we'll be able to go to some higher orders than 1 over r squared eventually. We could study more defect systems. Currently, we're looking at zero-dimensional defects, which are dual to giant gravitons. We're hoping to be able to have something to say about that at some point. And I'd like to work in some different space-time dimensions, for example, getting away from AdS 5, just because it would be nice to do things in other dimensions. That could be fun. So I guess I'm done here. If anyone has any questions, now would be a good time.
Thank you for a nice talk. Any questions?
There a reason why and straight from a simple pole to
So you can essentially think of it, so you can understand that if you were to look at the conformal Casimir for this thing, you can actually expand the conformal Casimir in flat space, and you'll find that you will essentially get a second derivative, which you would think would take you to a third order pole, but then you also multiply by 1 over s minus 2n squared. So you would, 1 over, 1 over s minus 2n. So just expanding the conformal Casimir can give you that directly.
You had this sort of MPL expression for G1. But would G2 also be MPLs? Do you have any idea of the structure?
Yes. So G2. Well, okay. In previous works, they computed G1 and G2 for other systems and found that both of them were MPLs. In fact, these are not just generic MPLs, but they're specific combinations of MPLs that are the real limit of single valued multiple polylogarithms. For the experts in the audience, that'll probably mean something to you. But yes, that structure is known to show up so far.
And any speculation on the weight?
The weight of those will be weight 6.
Weight 6. So it's 3K working.
Yeah, exactly.
Thank the speaker again.